Okay, so now we're at section 9.2. There are a lot of similarities between section 9.1 and 9.2, and some of the language is the same, but there's a lot of differences as well. The last two slides of this lesson will show you, we'll compare them side by side so you can see when to use which methods. So we're going to be obtaining a point estimate for a population mean. So here's a difference right here. State properties of students' t-distribution, determine t-values, construct and interpret a confidence interval for a population mean. We did population proportion in 9.1. We're doing population mean in 9.2. So 9.2 is a lot like 8.1, or it builds on what we did in 8.1. And we're going to determine the sample size needed to estimate a population mean with a specified margin of error. So instead of working with population proportions and p-hats, we're going to be working with population means here. All right, so let's just jump right in. So we already have what a point estimate is. This hasn't changed. It's the value of a statistic that estimates the value of a parameter. So remember, a statistic is a sample and a parameter is a population. So we use a point estimate, which is a sample that we use to estimate the value of the population. So for example, our sample mean x bar is a point estimate of the population mean mu. So we use x bar to estimate what we think the mean would be for the population, or as just an estimate of that population mean. Okay. So here's an example. So pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represents the weights in grams of 17 randomly selected pennies minted after 1982. So we're going to treat the data as a simple random sample, and we're going to estimate the population mean weight of pennies minted after 1982. You guys know how to find a mean. We just add them all together, and I'm not sure what happened here. Just a second. So I'm not sure what happened here. You know, we just add all those values together. I don't know why that says, L. This shouldn't say L. This should just be, sorry. So this should be 2.46 plus 2.47 plus, and then this right here would just be dot, dot, dot plus 2.45. So we add them all together, divide it by n, by the number there are. There were 17 numbers there. And then we get our sample mean. It's a sample mean because this is a sample of all the pennies. Obviously, we can't find the population because that would be every single penny out there. We would have to weigh every single penny out there, which is impossible. So we round the statistics to one more decimal point than the raw data. So our raw data is to 2 decimal points, so we're going to round our answer to 3 decimal points. So our point estimate for mu is 2.464. So suppose that a simple random sample of size n is taken from a population, so we're talking about a t-distribution. If the population from which the sample is drawn follows a normal distribution, the distribution of t is this right here. So this is kind of like finding a z-score. So remember our z-score, we would do an x minus mu over sigma. So here we have our sample mean minus the mu divided by, remember this is our new standard deviation that we calculated in 8.1, we calculated this new standard deviation. So we're doing the x bar minus mu divided by s over square root of n, the new standard deviation. It follows the student's t-distribution with n minus 1 degrees of freedom. We're going to talk about n minus 1 degrees of freedom pretty soon here when we are looking at our t-table, which actually something I should have told you to do right at the beginning. If you should go either into the back of your book or onto My Open Math and download that T and Z table, we're going to actually be on the second page today. We're going to be looking at table 6, which is a T distribution table. That's what we're going to be looking at today. So the n-1 degrees of freedom, we're going to be talking about that. When we calculated a sample standard deviation way back, I don't know, week 1 or 2, we calculated a sample standard deviation. We divided by n-1. So we divided by the n-1 degrees of freedom. So I looked and looked and looked to find a good explanation as to why we use n-1 degrees of freedom. And here's what I found online, and it doesn't make a whole lot of sense, but maybe it'll help you. It says whatever observations you choose to have, one last observation would be chosen by itself so that the mean of the distribution is equal to what is given. So essentially what you have is a freedom to choose a total of n-1 observations by yourself, hence the degrees of freedom n-1. Okay, so it still doesn't make a ton of sense, but that's what we use because our sample standard deviation is an estimate. We're estimating with n-1 degrees of freedom, and this is just what it is. So we're just going to accept it. We're going to talk more about n-1 degrees of freedom in a few minutes. So we're going to be comparing the standard normal distribution to the t distribution. So a t distribution is a distribution that is different than the standard normal distribution. So we're going to be looking at the z and z with a normal distribution, and we're going to look at t's with for the t distribution. Hold on a second here. So we obtained 1,000 simple random samples of size n equals 5 from a normal population with mu equals 50 and sigma 10. We're going to determine the sample mean and sample standard deviation for each of the samples, and we're going to draw a histogram for z and t. So we're already used to the histograms for z. A z table is when we have our normal distribution and we use our z-scores. So let me just show you. Maybe it'll help just to show you, and then we'll talk about it afterwards. So here's our histogram for z. Notice how everything is, the standard deviation clearly is not very much because our data is not spread out very much. It's a nice, beautiful bell curve. It's normally distributed. It looks nice and pretty. Let's now look at our t distribution. So our t distribution here, look how spread out that is. We have data way down here and way up here. We're not going to just be up to 3 standard, our z table. We go up to a z-score of 3. Look at the t-scores. T-scores are going way out here to 10 and negative 10, and it is crazy. So let's look at the comparison of the two. So the histogram for z is symmetric and bell-shaped with the center of distribution at 0, and almost all of the rectangles are between negative 3 and 3. Those z-scores, remember, 97.7% of our data is between negative 3, or 99.7, sorry, percent of our data is between 3 and negative 3 standard deviations, or a 3 and negative 3 z-score. So it follows a standard normal distribution. So let's look at our t histogram. It is symmetric and bell-shaped. The center of distribution is at 0, but the distribution of the t has longer tails. It's more widely dispersed. It doesn't likely follow a standard normal distribution, and the additional spread can be attributed to the fact that we use S, which is our sample. We're using a sample standard deviation to find t instead of sigma, which is our population standard deviation. That sample standard deviation causes it to be more spread out. The sample standard deviation is a random variable because that standard deviation is going to be different depending on which samples we choose. So it is going to vary. So it is a random variable because our standard deviation is going to be a little bit different for every one of our simple random samples. So we have more dispersion in the distribution of t. Here's the properties of a t-distribution, and it's going to look, some things are similar to our standard normal distribution and some are a little bit different. So the t-distribution is different for different degrees of freedom. So depending on how big our sample size is, our t-distribution is going to be different. That's what this means right here, this degrees of freedom. Depending on how many what our sample size is, our t-distribution is going to be different. It is centered at 0 and it's symmetric about 0. So this right here is the same as a using z and using a standard normal distribution. The area under the curve is 1. This is the same as what we've already been doing. The area under the curve to the right of 0 equals the area of the curve to the left of 0. Each one is 1/2. That is the same. As t increases or decreases without bound, the graph approaches but never equals 0. There's that asymptote again. Also, the area in the tails of the t-distribution is a little greater than the area in the tails of the standard normal distribution. We cannot use our imperial rule with a t-distribution. It is not accurate. So only with the z distribution or standard normal curve we can use the imperial rule. We cannot use the imperial rule with a t-distribution. We have further variability in our t-statistic than we do in our standard normal distribution because, once again, we are using S. We are using the sample standard deviation as an estimate of sigma rather than using our population standard deviation. All right, so as the sample size n increases, the density curve of t gets closer and closer to the standard normal density curve. This occurs because as the sample size n increases, the value of the sample standard deviation gets closer and closer to the actual standard deviation. We saw this in 8.1. So by the law of large numbers, as the sample size n gets bigger and bigger, our t-distribution is going to look more and more like a standard normal distribution. Okay. So here's a diagram that should help you. So you see this blue one here is our normal curve. So the bottom one here, this bottom one right there, whoops, the wrong pen color. So this bottom one right here is the furthest away from the normal curve. That one is when n equals 5. And notice this one right here, when n equals 15, we're a little bit closer to normal. As n gets bigger and bigger and bigger, we are going to get closer and closer and closer to that standard normal distribution. All right. So when we're looking at t sub alpha, the notation t sub alpha is a t-value, so that the area under the standard normal curve to the right is alpha. So we kind of did this. We did this with our critical values. When we were looking at critical values, our alpha was this area right here. So remember when we did 95 degrees of freedom, or sorry, our 95% confidence level, we would have two pieces right here, and this was our alpha, that area. It's the same thing here, except for right now we're only looking at the right tail. On this particular one, we're only looking at the right tail. So our alpha is the area of this tail right here. So that would be our alpha. We're going to find the t-value such that the area under the t-distribution to the right of the t-value is 0.2, assuming 10 degrees of freedom. That is, we're going to find t sub 0.2 with 10 degrees of freedom. So right now, I need you to pull out your t-table. I'm going to pull one up here, but I would like you to look at the t-table and follow along with me. So here's our picture over here. So we have this area right here is 0.2. So we're going to be looking at this column right here, because this is our 0.2 column. And notice how on my t-table right here, it says area in the right tail. So we're looking at table 6, area in the right tail. So we've got our area in the right tail is 0.20. So the difference here with the Z table, the difference is right here we have degrees of freedom. So we are going to look at the n minus 1 degrees of freedom. So our n is 10. Our n is 10, so we're going to look at 9. We're going to look at 9 because we do n minus 1 degrees of freedom. So you look at one number smaller than whatever degrees of freedom you are given. One number smaller than whatever our n is. Whatever your n value is, look one number smaller. So that means when we go here and we see, why did it give us the wrong one? Okay, so I'm guessing that, sorry about that, this example right here is our n minus 1. Yeah, so that must be our n minus 1. I apologize. So our degrees of freedom is 10, so we need 0.879. 0.879. So if I told you that, so here our n would equal 11. If n equals 11, when we're looking for our t value, we do n minus 1 degrees of freedom. So we have right here, we have 0.879. Okay. So find the t value such that the area under the t distribution to the right of the t value is 0.05, assuming 15 degrees of freedom. That is, find t sub 0.05 with 15 degrees of freedom. So go ahead and pause this or just find it, and then we'll do it together. So our n minus 1 here is 15. So we're going to go on 15 right here, and 0.05. And I will find where they meet, and my t value there is 1.753. So that's how we find that on the t table. Now our inverse norm does not work on this one, at least not that I have found. So you actually need to use this t table to find your t value. Make sure that you have the t table handy when you are getting ready to take a test or a quiz. Okay, moving on. So our sample data, we're going to be constructing a confidence interval. So we're going to be constructing a confidence interval. So our sample data is going to come from a simple random sample or randomized experiment. Our sample size is small relative to the population size, so our n is less than 5% of the population. The data comes from a population that is normally distributed, or the sample size is large. This right here is important. So the sample size has to be greater than 30, or we have to be told that the population is normally distributed, one or the other. So if your sample size is greater than 30 or the population is normally distributed, we can use this for our confidence interval. So this is very similar to what we did with the population proportion. This right here is how we are calculating our margin of error. The t alpha divided by 2 times s over the square root of n. So basically it is your critical value. It is your critical value right here times your new standard deviation. This is the standard deviation we learned in 8.1. And you take the x bar, so this is your sample mean, and you subtract and you add that new, or that confidence interval, that margin of error. You add and subtract that margin of error to get your interval. So let's do some math on that. And one thing important to note, that when we look at our critical value, n minus 1 degrees of freedom, and also make sure that you are dividing that that area, or whatever your confidence level is, divide it by 2. So let's do an example. This might help. Okay, so we're going to construct a 99% confidence interval about the population mean weight of pennies minted after 1982. For this sample, so this is our sample, so I put this into the calculator. I put it into that L1 column and used my 1var stats in order to get my sample standard deviation and my sample mean. So this is not the population standard deviation. This is not the population mean. This is the sample. So it's the S and it's the X bar. So I have the sample standard deviation and the sample mean here. We're going to use these to construct a 99% confidence interval. And how many pennies do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I have 17 pennies here. Well, this is ugly. I thought I fixed this. I apologize. I guess I did not fix this. Let me make it pretty real quick here. So we have x minus t alpha, and then we have plus t. This is an alpha. What's going on here? Okay, I'm having issues here. Okay, so this right here was multiplied 0.02 times. Okay, let's just do this math here. Okay, so we have 2.64 so where we're finding this 2.921. Where we're going to find this 2.921 right here is on your T table. So let me see if I can go back to the T table. Shoot, that's not going to work. Okay, so on the T table, you would need to look at we're looking at a 99% confidence level. So 0.99, 1 minus 0.99 equals 0.01. So we need half of 0.01. 0.01 divided by 2 is 0.005. So you will look in the column of 0.005, and n minus 1 equals 16. So you will look at 16 and 0.005, and you'll get 2.921. So that's where you're going to get for your critical value. Or at the bottom, at the very bottom of your T table, let me see if I can, the very bottom of your T table, so go ahead and scroll down. I don't have that up here. The very bottom of, actually the bottom of your Z table, no, I just lied to you. Sorry about that. So when we go 16 and you go to 0.005, go ahead and do this on your own because I just dropped the ball and I don't have that up on my screen. You should get 2.921. So hold on here. This is really ugly. I'm going to clear this out and I'm going to just rewrite this. So I have x minus t alpha over 2 equals, times that standard deviation, alpha x minus, and this is x plus. So we're going to do 2.464 times 0.02 divided by the square root of 17. I'm not sure what happened here. And then here is also times 0.02 over square root of 17. And so just do that math and you get 2.464. I'm going to put this in parentheses. It might be a little bit easier to read. There we go. So 0.02 over the square root of 17. Remember, this is that, what was that? What did we call that? So this is standard error, or the new standard deviation. Remember, I called that the new standard deviation in 8.1. So we end up with our margin of error, the 0.02 divided by square root of 17 times 2.921 is 0.014. So we add that and subtract that from our sample mean, and then we get our interval. So we can be 99% confident that the mean weight of pennies minted after 1982 is between 2.450 and 2.478 grams. So our population mean, we can be 99% confident that the population mean is going to be in this interval right here. All right, so let's take a look at another example. And I want you to try this example using the same math that I just used. So what I recommend doing with the data is put all of these numbers into the L1 of your calculator. So what we're looking at is the fuel economy in miles per gallon of different Ford Focus automobiles for 16 different owners. There's 16 here. So you're going to be looking at n-1 degrees of freedom on your t-table, so you'll look at 15. So this is a simple random sample of all Ford Focus automobiles, and we are going to assume that they're normally distributed. So I would like you to construct a 95% confidence interval for the mean miles per gallon of 2011 Ford Focus, and then interpret the interval. So go ahead and pause this. First thing I want you to do, though, is put that into your L1 in your calculator and get 1var stats, and that's going to give you your standard deviation, your sample standard deviation, and that's going to give you your X bar. So go ahead and calculate that, and then come back to me. All right, so let's take a look at this data. So we can put that into our calculator, and we get that just a second here. I had that up on my calculator a minute ago. You can get that where in the heck did I just put that data? Okay. So with all of that, we get that our X bar is 36.8, and our S is about 2.92. So we got 36.8 and 2.92. So now we need to calculate our confidence interval. So we would do 36.8. Look at your t-table. On the t-table, you should be able to look at that and look at, because we have 16 here, we need to look at 15, and 0.05 divided by 2 gives us 0.025. So you'll be looking at the 0.025 and 15 on your t-table. So 15 and 0.025, our t alpha over 2 equals, see here, t alpha over 2, 2.131 from our t-table. We got 2.131 for our critical value. That's our critical value. So we're going to do 36. I'm going to do this in a different color because I didn't leave enough room to do math on here. So I'm going to do 36.8 minus 2.131 times 2.92 divided by the square root of 16. Let's calculate that margin of error first. 2.131 times 0.92 divided by square root 16, which is probably 4. So I got 36.8 minus 1.56 and 36.8 plus 1.56. So 36.8 plus gives me about, okay, I'm just going to go down to the bottom. I have 38.36 approximately, and my upper interval 36.8 plus 1.56, and I have about 38.36. Beautiful. Okay, so I have 38.36, and I did plus twice. Man, I'm losing my mind. Okay, let's try this one more time. 36.8 minus 1.56 equals. Sorry about that. 35.24. So 35.24 is my lower and 38.36 is my upper. Let's do this an easier way. Let's use our calculator. So the interpretation of this would be that with 95% confidence, I can say that the population mean of the Ford Focus automobiles would be between 35.24 and 38.36. Okay, let's take a look at our calculator. So we're going to go, first thing you want to do is you want to put all of your data in the L1. So you know how to get here. We've been doing this the whole time. So put that into the L1. Then go to stat right here. Whoops. Clear the pen markings. So we're going to go to stat right here and then go over to tests. Just like we did on the last one, go over to tests. Highlighter is not working well. And scroll down to T interval. Once again, there are a lot of things that have T in them. We want T interval. When you click on that, there's two different options. So this option, the option that says data, is the one we're going to use because we have our data in the L1. If you put data in the L1, then you're going to use data here because it will pull all of that. It will find the standard deviation, it'll find the mean, it'll take care of all of that stuff for you. If you do not have that, you're going to click on stats. If you're given standard deviation and you're given the mean, click on stats and you'll just put those in there. So if you have the data, go to data. If you're given the stats, go to stats. So you're going to want your lists L1 because that's where you put your data. Frequency is 1. It's always 1. And then your confidence level, we're looking for a 95% confidence level, so put 0.95. Next, when you hit enter, you hit calculate, you will get your confidence interval. 35.246 to 38.354. How are those compared to our numbers? They're really close. They're really close to our numbers. So, and this even shows you that your X bar was 36.8 and your standard deviation was 2.9. Did we have that? That's what we got. Good. It better be because I got it from this calculator. And it also shows you that your N is 16. So you would just be able to give this confidence interval right here. Be able to say with 95% confident, I'm 95% confident that our population mean will be in between those two values. All right. Well, this didn't turn out good either. I thought I fixed all of this. Sorry about that. Okay, so let's take a look at determining our sample size. So I'm going to make this beautiful I'm going to attempt to make this beautiful. I apologize. If you look at the PowerPoint that is on my Open Math, it should be much prettier for you. It should look all nice, and I'm going to erase this and start over because I don't like it. So this is multiplication. So it's your critical value with z times the sample standard deviation divided by your margin of error squared. We have to use z here because we don't know n. Since we don't have n, we can't calculate a t value because the t value is dependent on how many degrees of freedom we have. So we have to use our z critical value in order to calculate the sample size that we need. This right here, I'm just reminding you that that's how we calculate a margin of error if we know our sample size, and that's how we can calculate our margin of error. All right, moving on. So we're going to go back to the pennies, and we're going to do this math. So how large of a sample size would we be required to estimate the mean weight of pennies manufactured after 1982 within 0.005 grams with a 99% confidence? We're assuming that sigma is 0.02. So we're saying that our population standard deviation is 0.02. We are assuming this. So let's take a look at this. See, this turned out okay. So we were looking for a 99% confidence level. So because of that, we take our alpha was 0.01, divided by 2, we get 0.005. Looking at the critical values at the bottom of our z table, we get 2.575. This is our critical value. We already are estimating that our standard deviation is 0.02. We're keeping that. We were told that we are looking within 0.005 grams. That's our margin of error. So we want our critical value times the standard deviation divided by our margin of error and then square that value. So here's our math right here. Once again, we have to round up because 106 is not high enough because it has to be at least 106.09. So we always round up to the next higher one. We are not going to get that 99% confidence unless we have this right here higher than that, at least that amount. So we're going to go up to 107 because we cannot look at 106.9 pennies. Impossible, 0.09 pennies. So now, I would like you to go back to the Ford Focus data. How large of a sample is required to estimate the mean miles per gallon within 0.5 miles per gallon with a 95% confidence level? So I would like you should still have that Ford Focus data in your calculator. So go ahead and do it on your calculator with the, go ahead and look at your calculator and find my n. Go ahead, pause this, come back and we'll do it together. All right. So we are looking at z times s over e and then squared. So our z for the 95% confidence level, our critical value is 1.96. Our standard deviation, sample standard deviation, is 2.92. That's what I'm going to use, 2.92. This is a multiplication. Divide that by our margin of error is 0.05, and then we will square that. So we have 1.96 times 2.92. Well, that looks like a really big number. I need to try this again. So we have 1.96 times 2.92 divided by 0.05. No, that's my problem right there. I knew that something was wrong. I apologize for that. 0.5. That makes a difference. Okay, so this gives me 131.02. So once again, I need to round that up. So I need n equals 132. I need to sample 132 Ford Focuses in order to have a 95% confidence level with 0.5 plus or minus 0.5. So my margin of error would be 0.5 miles per gallon. So then if I sampled that many, I'd be able to tell with a 95% confidence that the mean miles per gallon of a Ford Focus would be between whatever my confidence level is, be plus or minus 0.5 of that mean. Okay, so let's jump to the comparisons. So the difference between what we did in this section and what we did in section 9.1. So section 9.1, here's a couple of words that we need to look at that will help us. So we obtain a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. The word proportion is important here. Section 9.2, construct a 95% confidence interval for the mean miles per gallon of a 2011 Ford Focus. So we use the methods in 9.1 if we're looking at proportions. 9.2 if we're looking at means. Okay, let's do another comparison. So this is for sample sizes. So what sample size should we obtain if she wishes her estimate to be within 3 percentage points with 90% confidence, assuming she uses 2,000 estimate obtained from a census 2000 supplementary survey of 82.4%. All right, so here I'm using a previously, let me see here, how am I going to do this? Previously obtained data. I have this right here. This is a proportion. It's a percent that we're looking at, and we're looking at 3 percentage points. So that's something to look at. Here, how large a sample is required to estimate the mean miles per gallon, that word mean again, with 0.5 miles per gallon. So over here in 9.1, we're looking at proportions in percents, and here we're looking at actual numbers and mean miles per gallon. So the word mean is really important. 9.2 is all about the means. 9.1 is about proportions and percents. Hoping this really helped. I know I stumbled a little bit. Sorry about that. It's after 10. I wanted to get this done. Please send me your emails and messages. I'll do my best to get back to you as quickly as possible. Thank you.